In this section, we're going to look at radioactive decay. So not all things that we can think of as resources are good. There's some things like nuclear waste that we want to become exhausted. The radioactivity of materials decreases naturally over time. A radioactive substance emits particles and decreases in quantity at a predictable continuous rate, so we can figure out how much is going to be left after a certain amount of time. Radioactive materials have an exponential decay, which we saw in section 21.5 as growth with a negative rate of growth. So if we draw a graph of what that's going to look like, if we have, I'm going to draw my axes here. If I've got a certain amount of a resource that I start off with, then over time, at first it's going to decrease steeply, but then it's going to flatten out and get close to zero, but never quite actually make it to zero over time. So let's look at the decay constant. In section 21.5 we saw a negative growth rate written as R. In this section we're going to write that as negative lambda. This is the Greek letter lambda here. And the positive quantity, lambda without the negative, is called the decay constant. The decay constant for a substance that decays exponentially is the proportion of the substance that decays per unit time, and we're usually probably going to be looking at years here. So if we want a formula for the amount of a radioactive substance that's left after a certain amount of time, we can use this formula. A is equal to P, which is the original amount of the substance, times e to the negative lambda t. And this is the same as the continuously compounded interest formula from section 21.3. We've just got the negative lambda here instead of an r. So another number that we're interested in is called the half-life, and that describes the rate of decay of a substance as well, and that's written as h. The half-life of a substance that decays exponentially is the time that it takes for 1/2 of the quantity to decay. So that's the time after which only 1/2 of the original amount will be left. A substance that decays exponentially never completely vanishes even after millions of years. So in my little graph there, it keeps getting closer and closer to zero, but never quite gets there. And we can relate half-life to the decay constant by using this equation. The decay constant lambda times half-life h is equal to the natural log of 2, which is about 0.693. So with this equation, if we've got lambda, we can find h, or if we've got h, we can find lambda. So if I divide both sides by h, then the decay constant lambda is equal to the natural log of 2 divided by h. If I divide both sides by lambda, then I can write the half-life h as the natural log of 2 divided by the decay constant lambda. So if you have one, you can figure out what the other is. So let's look at an example. Iodine-131 is a radioactive isotope that is produced in nuclear reactors and nuclear explosions. There is great concern about the release of iodine-131 across Japan and the Pacific after the earthquake, tsunami, and nuclear reactor disasters in Japan in early 2011. The half-life of iodine-131 is 8 days. If you start out with 100 grams of iodine-131 now, then in 8 days you will have only half that amount, or 50 grams. So we want to figure out how much iodine-131 will remain after 40 days. So to do that, I'm going to just draw a little chart. Down here, I know that every 8 days the amount is going to be cut in half. So I've got my chart here. I'm starting out at 0 days. I know I've got 100 grams. And then I'm going up in 8-day increments. So after 8 days, I'll have half as much, which will be 50 grams. 8 days later is 16 days, and I'll have half of 50 is 25 grams. 24 days is 8 days after that, and I'll have half of 25 is 12.5 grams. Another 8 days takes me to 32 days. I'll have half of 12.5 is 6.25 grams. And then finally I get to 40 days, which is what I'm interested in. And I take this and take half of that again. That's going to give me 3.125 grams left of the original 100 grams after 40 days. So it goes away pretty quickly, actually. Another place that radioactive decay is used is in carbon-14 dating. Plants and animals continuously absorb carbon-14 during their lives. Once they die, no new carbon-14 is absorbed, and the carbon-14 that is present decays. Carbon-14 dating is a method used to determine the age of organic materials. And these can include mummies, charcoal from ancient fires, parchment, and cloth, so used a lot by archaeologists. Because we know the concentration of carbon-14 in living things, and we know how long it takes carbon-14 to decay, we can calculate from a sample how long ago a plant or animal was living. And to do that, we're going to look at this chart here. So the half-life of carbon-14 is 5,730 years, and scientists measure how fast the carbon-14 is decaying in a sample to find out how old that sample is. So here they've got the rate of decay in the last column here. So if the sample is new, it's got 0 half-lives, its age is 0 years, then the decays per hour per gram of carbon is going to get given by 1/2 to the power of 0, the number of half-lives, times 814. So you'll see 814 decays per hour per gram of carbon for a new sample. And then for each half-life, we go up by 1 half-life in the first column here, and then that's given in years in the second column. And in the third column, the decay rate is given by 1/2 to the power of whatever the half-life is times 814. So we want to find out how many atoms would be decaying per hour per gram of carbon after 45,840 years. So I'll give myself a little bit more room here down at the bottom. So the first thing I need to do is figure out how long that is in half-lives. So I'll take 45,840 and divide that by 5,730 to see how many half-lives that is. And that turns out to be 8 half-lives. Alright, so that's 8 half-lives. Then if we follow the pattern on the table here, then my decay rate is going to be equal to 1/2 to the power of 8 times 814, and that is equal to 3.18 atoms per hour per gram. So you can see also, if you look at this column here, you can see that for each half-life the decay rate is cut in half. So we start out with 814. After 1 half-life, that's 407, which is half of that, and it keeps going in that pattern as we go down. There are some other uses of radioactive decay. Radioactivity is not always a bad thing. One concern about nuclear power is whether enough uranium could be mined for a nuclear future. So people who are interested in nuclear power as an alternative energy source would need to think about if there's enough radioactive materials available for nuclear power to be a good solution in the long term. Radioactive isotopes are also used a lot in medicine for medical imaging or as tracers in the body. Technetium-99m is used in 20 million diagnostic procedures per year, so it's a very useful isotope. 5 nuclear reactors produce molybdenum-99, which is an isotope that decays into technetium-99m. In 2010, 2 of these reactors closed for repairs. Because these isotopes have very short half-lives, 66 hours and 6 hours respectively, having a constant supply of these isotopes is important for medical practice. So that finishes up this section, things you should know. You should be able to know the definitions of decay constant and half-life and how they are related. Use the decay function given a decay constant to figure out how much of a radioactive substance remains from the original amount after a certain period of time.